Learn like a pro.
Welcome. Today, we are going to level up your chemistry skills and master one of the trickiest topics out there, figuring out what actually gets made when you pass electricity through a salt solution. Think of it like a game of ions, and we're going to learn the rules so you can win every single time.
Okay, so let's just dive right in. Now, you probably remember the simple case, right? You take something like sodium chloride, just regular salt. You melt it down, we're talking molten, no water, and you zap it with electricity. It's totally straightforward. You've got your sodium ions and you've got your chloride ions. The positive sodium zooms over to the negative cathode. The negative chloride heads for the positive anode. Boom, you get sodium metal and chlorine gas. Super easy.
But what happens when we add water? Well, the game changes completely. Suddenly, it's not a simple two-horse race anymore. Nope, it's a chaotic four-way competition because water itself decides to jump into the action. And this is where things get really interesting. This is what we're going to master today. So here's our game plan for today. We're going to look at why water makes things so tricky. We'll meet our 4 ion competitors, learn the all-important rules of discharge, run through a classic case study, and then you'll be ready to make your own predictions.
All right, let's get into our first section. Why does adding water change everything?
So here's the absolute key. Electrolysis is just using electricity to break a compound apart, right? But in an aqueous solution, that just means dissolved in water, you've got 2 things that can be broken down. You've got the salt you put in, and you've got the water itself. Both of them are potential candidates. They're both fair game for the electricity.
Okay, so if we've got a 4-way race on our hands, we need to know who the competitors are. Let's meet the lineup.
And here's the secret player. Water isn't just sitting on the sidelines watching. Oh no, it is an active participant. A tiny fraction of water is always breaking apart on its own into H+ ions, so hydrogen ions, and OH- ions, hydroxide ions. And guess what? These 2 new ions jump right into the race for the electrodes.
So, have a look at this table. It really spells it out. Whether you're dissolving sodium chloride or copper sulfate, it doesn't matter. You always end up with 4 ions in the mix. You get the cation and anion from the salt, and you get H+ and OH- from the water. Every single time, it's a 4-way showdown. All right, so with 4 ions all competing, it's chaos. We need a rule book. We need a way to predict who's going to win the race to each electrode. So how do we do it? Okay, let's try an analogy to make this stick. Picture a really busy subway station at rush hour. The ions? They're all the commuters, scrambling to get on the train. And the electrodes, those are the train doors. Now, not everyone gets on at once, right? There's a big rush, and only the ones who are quickest, or maybe just the ones who are crowded right up against the door, get through first.
Okay, so here are the 2 fundamental rules of the game. First, let's look at the cations heading to the negative cathode. This is a battle of reactivity. The rule is simple. The ion of the least reactive metal gets discharged. It's basically an energy game. The easiest one to turn back into an atom wins. Now, over at the positive anode with the anions, it's a bit more of a fight. Usually, hydroxide wins, but there's a special rule. If you have a concentrated solution of a halide, like chloride or bromide, then the sheer number of them can overpower the hydroxide and they win instead. Concentration is the key.
So this right here, this is your foolproof step-by-step guide, your decision-making flowchart. Step 1, just identify all 4 ions in the solution. Step 2, look at your 2 positive ions. Find the one that's lower on the reactivity series. That's your winner, at the cathode. Step 3, now look at the negative ions and ask the most important question, is this a concentrated halide solution? Step 4, if the answer is yes, the halide wins. If the answer is no, hydroxide wins. Just follow these 4 steps and you will get the right answer every single time.
All right, we have the rules, we have the flowchart. Now let's put it into action with a classic chemistry showdown. Dilute sodium chloride versus concentrated sodium chloride.
This table lays it all out beautifully. Look at the cathode first, the negative one. In both cases, H+ wins over sodium because hydrogen is less reactive. So we get hydrogen gas no matter what. But now, look at the anode. This is where the magic happens. In the dilute solution, the normal rule applies. Hydroxide wins, and you get oxygen gas. But crank up the concentration, bam, the chloride ions take over, and you get chlorine gas instead. That's the concentration effect in action.
So to spell it out, in that dilute solution, the standard rules win the day. There just aren't enough chloride ions hanging around to put up a good fight. So the hydroxide ion, which is easier to discharge, steps up and produces oxygen gas.
But in that concentrated solution, it's like our subway station analogy. The platform is packed with chloride ions. They just completely crowd out the few hydroxide ions trying to get to the door. So even if it takes a little more energy, just by sheer numbers, they win the race to the anode and get discharged, forming that chlorine gas.
And hey, here's a neat little practical tip for you. That oxygen you produce in dilute solutions, it's pretty reactive. If you're using carbon or graphite electrodes, that oxygen will actually start reacting with the carbon, essentially burning your electrode away into carbon dioxide. So over time, you'd have to keep replacing it. Kinda cool, right?
Okay, so we've mastered predicting what gets made. That's awesome, but we can take this to the next level. Let's see how we can actually calculate how much of each product we're gonna get.
Believe it or not, we can use these half equations to figure out the exact ratio of the products. And the whole thing hinges on one simple principle. Electrons are conserved. The number of electrons lost at the anode has to exactly equal the number of gained at the cathode. So let's take copper sulfate as an example. At the anode, making 1 mole of oxygen releases 4 moles of electrons. At the cathode, those 4 moles of electrons can be used to make 2 moles of copper, because each copper ion only needs 2. So what's the final ratio? For every 1 mole of oxygen, you get 2 moles of copper, a 2-to-1 ratio every time.
All right, let's wrap all of this up into the ultimate cheat sheet. Seriously, screenshot this, write it down. This is your key. At the cathode, it's simple. The least reactive cation always wins, giving you either a metal or hydrogen. At the anode, you have one question to ask. Is it a concentrated halide? If the answer is yes, you get the halogen gas. If the answer is no, you get oxygen. That's it. That's the whole game. Okay, before you go, let's quickly cover the common mistakes, the traps people fall into. The number one biggest mistake, forgetting to check the concentration. It's the whole game changer for the anode. After that, people mix up the reactivity series. They forget which electrode is positive or negative, or they just completely forget that water is even in the race, adding those H+ and OH- ions. Avoid these, and you'll be golden.
All right, you're the expert now. You've got the rules, you've got the cheat sheet, so here's your final challenge to test yourself. Imagine you're doing the electrolysis of a concentrated solution of hydrochloric acid, or HCl. So, what are your 4 ions? Who's going to win the race to the cathode? And, the big question, who wins at the anode? Pause and think it through with the rules we've covered. I know you can figure it out.